today it's my pleasure to have Chris Rackauckas from MIT here to speak to us. He's going to be speaking about stiffness in scientific machine learning. So Chris got his PhD at the University of California in Irvine in 2018. And I think I became aware of Chris around the time that he graduated, because he's now a applied math instructor at MIT. Chris is well known for his software development. Particularly, he's the creator and the lead developer of a package called Differential equation.jl. This is a Julia package that kind of puts in a load of DE solvers. It's really quite fantastic. I found out today he does a bunch of other things as well. Like he has this Puma's Julia package, which maybe he can tell us 1 minute about. I didn't really understand exactly what it did. But anyway, so today he's going to be telling us about stiffness in scientific machine learning. Thank you very much for joining us, Chris.
Chris, you're still muted.
Yes, that wouldn't work very well. Yeah, so thank you for the introduction. That's a fairly good introduction to a few things here, in that the way I usually like to describe where scientific machine learning, why it's such a big deal and why it's so interesting, is because one of my other backgrounds is not, so I'm an applied mathematician, but my other hat is in the School of Pharmacy. And one of the things that's really interesting is people are trying to look into how you can do models that are automatically adaptive, by using things like deep learning. But it turns out that the medical field is one of those areas that is very difficult to actually do deep learning on, because you can't just train a neural network with one clinical trial to then dose people correctly in the second, right? That's pretty unethical. You have to make sure that you kind of have an idea that you're doing it correctly and safely the first time, right? So one of the big issues with machine learning is that deep learning learns everything from the data. And so it really requires quite a bit of data to work correctly, right? And so what we really need to do is we need to come up with some kinds of algorithms that can, get it right the first time by using all the scientific knowledge that we have. And where scientific knowledge is held is in models, right? Essentially, when we write down these models of, for example, the canonical Wnt pathway, this is not just one student's PhD thesis, but this is many students' PhD theses, which are showing each of these different parts of the pathways, or how beta-catenin enters the nucleus, right? So one of these flowcharts, one of these diagrams, one of these models, you can kind of think about it as an aggregate of hundreds of thousands of data sets, right? And so in some sense, we could do machine learning with this. We just don't have the heterogeneous Google-style data set to match this idea. But scientific models themselves are a set of information and a set of data. And so what we're doing with scientific machine learning is model-based data efficient machine learning, where we're taking the big data procedures, like here I'm showing a single cell RNA-seq result, and we want to mix that kind of big data procedure with the data that we actually have encoded in these scientific models that we see in systems biology, that we see in computational fluid dynamics. Every one of these pieces where we have a lot of differential equation information for how things evolve over time, but it doesn't give a full specification, mostly gives a partial specification. Now, one of the interesting things is not just what this problem that we have with data, but it's actually how machine learning works. Doesn't necessarily mean that machine learning is doing science, right? I had one professor that I worked with before like to call a lot of machine learning on science non-hypothesis based science, to kind of highlight this fact that if you just have machine learning do prediction, it doesn't necessarily tell you how the system works, right? So what we really need to solve with machine learning to make it do solve scientific problems is we need to make it do things like tell us how to fix our model when we have new data, right? So if we have a new data source and a machine learning and a neural network predicts better, well, why is it predicting better, right? Is there a chemical reaction that we didn't know about? Is there some kind of, is there some chemical reaction in there that we specified that isn't actually happening? Like what in the model should we be changing now that we found that with this data source that our model must be incorrect somewhere? Right. How can we, another problem is if we're going to be using a lot of models, can we use machine learning to accelerate these models? Can we use it to generate hypotheses about what kinds of data we should go get back and get? Like, if there's multiple models that are predictive, multiple neural networks in different ways with different parameter sets that are all predicting well, are these predicting different models? And is there a set data set that would tell us which one is more correct? All these problems are these problems that if when you're trying to do science, you would naturally do with a mechanistic model, and we're trying to figure out how to solve these kinds of problems in a way that has mechanistic models mixed with machine learning. And so the goal here was really to provide one mathematical foundation for automated scientific machine learning. And so that the field could kind of have a foundation that is as simple as, stiff ODE solvers, right? So my background is in a lot of work in numerical differential equations. And one of the things that's really nice about numerical differential equations these days is that, most people don't know how most of the software works. They just type in ODE15S with their problem, and boom, then it's able to solve the stiff ODE, right? Can we do this with a form of scientific machine learning? So, you give it part of a model, you give it some data, and then you say, tell me what the rest of the model should be. Automatically discover the missing physics. Can we get this kind of problem to the level of where stiff ODEs are optimized, right? You still need to tweak tolerances, but it's pretty much there. So this is what we've been working on in the Scientific Machine Learning Software Organization, the SciML organization, where the differential equation solvers are really the core. But what I'm really going to be talking about is this diffeq flux component, which is used then to build all the other components. It's diffeq flux is kind of the core of the portions which are all about model discovery. I'm going to kind of describe how they end up in the central role, even though they kind of feel like they'll kind of feel like a niche idea to start, but then we'll start to see how many different algorithms can start to be expressed in their form. Um, and so the real question is, how can we condense scientific machine learning, this idea of doing models with machine learning and all the different ways that you can think about doing it? How can we express it as one single method so that we can sit down, understand the numerics of the problem and make it stiffly robust? This is what we did through the universal differential equation method. So the where you get started with this method is just to understand the universal approximation theorem, which is in a nutshell, it's basically that a neural network can be an approximator to any Rn to Rm function. So if you have a function that's Rn to Rm, you can find with a sufficiently large neural network that you can tweak the parameters around and you can get epsilon close over the whole space that it's supposed to predict on. Right, so that you can make this more formal, but really the idea is that if you have a large high dimensional function, like for example, if you have a one-dimensional function, you could do this kind of thing with a Fourier expansion or a Taylor series. But it turns out that a neural network is a really nice way to do this in very high dimensional spaces. So you can represent missing functions, you can represent functions that you don't know about as problems where you now just have to find discrete numbers of parameters to be able to represent that function, and we can then use this to be able to do all sorts of interesting things. And so the universal differential equation is just a differential equation which is defined in part by universal approximators. So you say there are parts of the function that I know and I'm specifying some mechanisms, but then there are functions which I don't know, which are specified as functions that can literally represent any possible function. And then what we're going to do is we're going to use a technique to recover these the parameters of this that parameterize these universal approximators, and this will then tell us what the missing parts of the models are, or what nonlinear closure relationships are, and all these types of problems. And so the first the way I really like to dig into this is I'm really a fan of, do the easiest example to be able to explain the concept first. And so the nice example that we have is actually something derived from a recent publication we had in Cell Patterns, which is about using universal differential equations in epidemic models. So the way this looks out is we really ask the question of, when you're trying to understand what's different about the pandemic between different countries, basically we know that every country had a different outcome. And so what we really want to understand is how is the model different between the different countries, right? And so the first thing that you might want to try is you just say, I'm going to make u prime equal a neural network because a neural network is a universal function approximator. And so, this is saying that u prime equals any possible f, discover what the f is. I'll go into at the end of the talk, or at the end half, I'll be discussing how we actually find what the parameters are of these neural networks embedded inside the differential equations. But this is the now classic neural ordinary differential equation where we just say u prime is just completely given by a neural network. And while it is able to find the dynamics on the data that we train it on, so from 0 to 21 days, we train it on a given, the data from here, and then we extrapolate in the future. You see that it doesn't extrapolate well because it's, these are the properties that you'd expect with neural networks, right? It's an over parameterized model. It's then trying to predict data in a regime that wasn't trained on, and so therefore it gets it completely wrong. And there's many different examples and many different papers showing that this is what happens, right? So how can we make it so that way this can predict better with the same amount of data? So this is where we can get to the universal differential equation, right? So it's a differential equation which is defined in part by universal approximators. And for the case with COVID, right? We know, I mean, a lot of people even in this room can probably know a lot of the details about how the model would work, right? So it's pretty well established what is the rate of recovery from COVID-19. It's pretty well established what is the probability that someone will be hospitalized if they have the disease, right? So there's a lot of information in here, such as we can write down a pretty approximate models, an SEIR model, which is susceptible, exposed, infected, recovered. There's also this D term, which is for infected but hospitalized, and then there's integrator terms that you could ignore. But this is your standard epidemiological model for saying here's how the disease flow works. Except the thing that we don't know exactly what to do with, for COVID-19 is we don't exactly know the rate at which people get exposed, right? Because the exposure rate is dependent on whether people are wearing masks, whether they're really risk adverse and staying home, right? It depends, and it can change country by country. It change county by county, right? So we have a pretty approximate model that says we know the rate at which people recover from the disease, and we know a lot of these details, but what we don't know is exactly how people get exposed to the disease. So if we can automatically discover what the exposure function should be, then we'd have something that can predict fairly well. And if you do it in this style, right, if you do this style of, I'm going to make my neural network very small and really capture just the pieces of uncertainty in my mechanistic model, you can see that you get a lot better extrapolation. So here is, still from just 0 to 21 days worth of data, we train the neural network that's embedded within these mechanistic equations, and then we're able to extrapolate out to around 40 days, right? And the reason why it's able to do so well is because you should expect a lot of the asymptotic properties of the model to be correct because we've encoded all those pieces in there, right? It's the neural network is really just handling a much smaller piece. But this isn't all the way, so how can we do more? We can start to pull in some ideas from other parts of dynamical systems literature. So Stephen Brunton and Nathan Kutz does some really interesting stuff with sparse identification of dynamical systems, which is essentially how can you take data about a dynamical system and have it spit out LaTeX, which is the dynamical system that you should have known about in the first place. If you were to directly do this on just 21 days worth of data, which is exponentially increasing, you don't get fairly good results. And the reason is because, well, it's just not very much data for such a difficult process, right? And so this is a very nice method if it works very well if you have sufficient data to be able to support it. But I just described a way to be able to encode more scientific information. So now what we can do is we can put these pieces together, right? Where we say let's find let's write down a mechanistic model where we have the terms that we don't know about represented by a neural network. We fit these neural networks within the differential equation, and then we pull them out and we can fully analyze them and say, let's do a sparse regression against a basis of symbolic equations, discover what those symbolic equations are. And here what I'm showing is that, if you do this process, then what you can do is you can find that these missing neural networks can be best approximated by this set of symbolic equations. There's a few properties that you get out of that. It tends to extrapolate much better, right? It's not extrapolating perfectly. You can see it does diverge, but it tends to extrapolate a lot better, and because this is one of these properties where low dimensional approximations or low dimensional polynomials tend to be much better extrapolants than very high over parameterized models, right? So finding a sparser form of the model tends to give quite a bit better prediction properties, but then it also gives us some hypotheses, right? So for example, we have that I is the infected individuals and D was the infected individuals who were hospitalized. Well, what we allowed this neural network to be a function of S, I, and D, but when we sparsify, it says that it's only a function of S and I, right? You see that D doesn't actually show up in here, which means that the exposure is not related to the people who, the percentage of the population that is hospitalized, which tends to make sense because most of the exposures are coming from people who are, asymptomatic or less symptomatic, who are still, in the general population, just spreading the disease around, right? And this kind of hypothesis kind of naturally comes out of the way that we've found mechanistic equations from the embedded neural networks. I'll add one little detail in here, and the reason why we do this with the neural network embedded first is because neural networks and local optimization have some very nice properties where we can then just use direct local optimization to find whatever parameters describe a function in here. We can pull it out and then do your fanciest, genetic algorithm to be able to, find in an unbiased way what the symbolic equations are that match the neural network. This two-stage process really stabilizes the result. And this is really where we end up at this. This is the first use case for universal differential equations, which is about ML augmented scientific modeling, where we use it to discover models and use it to augment models, right? So we identify parts of the model which have high uncertainty. We train a neural network to capture the missing mechanisms through this neural network embedded in. Then we sparse identify to find the mechanisms, and then we can go back and we can verify the mechanisms. We can ask questions about how it extrapolates, and we can start to ask questions like, what data would we be required to be able to validate whether this term is correct, right? Because if you find that there's a quadratic term and it's a chemical reaction network, then you're actually making a prediction that there's some kind of feedback term, right? And you can then go back and actually double check what the neural network has discovered that is required to be able to fit the aggregate data. So we found that this kind of approach is able to do some pretty wild things. So here, for example, is a Lockville-Terry equation where we gave it the information about what the linear behavior. So we said, there's a linear exponent, there's an exponential increase in the amount of rabbits if you leave them alone. There's an exponential decrease in the amount of wolves if you leave them alone. And now, given this data set that we have from a solve of a Lockville-Terry equation, discover what the nonlinear terms would be, and then extrapolate that out in the future. And you could see that if you do that with just a very small amount of data, it's able to discover that the unknown interaction terms are these quadratic terms. And once it's discovered the right differential equation, it's able to predict in the future and draw this line right through the data points, and so even though it did not see in the data that it was cyclic, right? It's because we given enough other alternative information for it to be able to discover that it had to be, had to have this quadratic term within the differential equation. And then because it has to have that quadratic term in the differential equation, then it needs to have a cyclic solution because that is the differential equation solution, right? So really the key idea here is that, the data doesn't tell the whole story when we're adding in such scientific or mechanistic information to be able to augment what's going on with the data. And we're making use of this in a particular way to be able to optimize materials for battery powered aircraft. And we're basically using these techniques in a closed loop to be able to do, try to discover what better models are for these materials, and then using that to, go back and once we understand the better mechanisms for how these materials are causing, better or less battery degradation, then we can actually go try to find the materials which degrade less. And some of my colleagues have actually demonstrated that we can take a state-of-the-art battery model, so one of these DFN types of models, and be able to increase their ability to predict degradation by about 19% by, you start with the state-of-the-art model, you augment it with neural networks in the places with the highest uncertainty, you train this on a bit of data, and it's able to then predict on different parameters or different materials whether or the rate at which it would decay. So that was all about discovery of ordinary differential equations. Now let's move on to something more difficult than ordinary differential equations. So the first step that I always like to take is the differential algebraic equation, because there's always a question about how can you encode physical constraints in a machine learning framework. And using this kind of idea gives you a fairly flexible way to be able to choose whichever constraints you want, right? So you can do something like say, I have three species of a chemical reaction network, Y1, Y2, Y3. These species are actually, there's one molecule which is conserved between all of them. And so I better have that, 100% of that molecule always exist. And so over time, I have a dynamical constraint that, Y1, Y2 plus Y3 is always equal to 1. But now I encode that I know that there is a linear reaction that changes Y1 to Y2, but there must be some other nonlinear interactions. Please discover what those nonlinear interactions are for me. And this would just be a universal differential algebraic equation, which you can represent in its mass matrix form. And then once you can write it down in a mass matrix form, then you can use the techniques that we've developed to be able to train the embedded neural networks. And so this idea of I want to be able to conserve a quantity over time falls into this idea, this method that we're essentially calling a model or discovery method. But you can also see how you can use this to be able to basically write down recurrent neural networks which satisfy whichever constraints you want. Now, the next thing that you can do is you can start to say, well, we have ordinary differential equations and differential algebraic equations. So how do we move this to partial differential equations? And it turns out that there's a relationship between partial differential equation discretizations and convolutional neural networks, right? The relationship is that convolution operations of a convolutional neural network are exactly the same thing as a PDE stencil, right? So essentially, if you what a convolutional neural network does is it lets you give it, or it tries to find what the coefficients would be of a stencil operation, and then what it does the um, how you calculate that value there is you do the linear combination between the stencil coefficients and the coefficients of the image, and then so you do like 1 times 1, and the black numbers times the red numbers in the square, and then you move the square one over, and that's how you do this convolution, right? It turns out that if you look at the discretization of something like the Laplace equation, it turns out that that's just doing a stencil, 1, 1, 1 minus 4 all across a image, which is the current data of the differential equation. And so you can then start to use this relationship to be able to turn back and say, how can I discover what the partial differential equation is that generated my data? Well, you can use a combination between neural networks and convolutional layers and say, well, if I have spatial temporal data, I can represent my derivative operators by convolutional terms. I can represent my nonlinear terms by these neural networks. And when I when I do this training process, what comes out of this is it says this convolutional layer is just something that has coefficients 1 minus 2, 1. So therefore, it must be the discretization of the diffusion, and the other term is it finds a neural network that is the nonlinear term, where that nonlinear term, if you do the sparse identification to it, then you find that it's a quadratic term. And so you can take in some spatial temporal data, throw it in, and train these embedded neural networks inside of these differential equations, and what it basically spits out is that you have a quadratic term plus a diffusion term, and so this is a Fisher KPP equation. This is actually a very interesting property of what's going on here too, is that this is a fairly data efficient method because we've reduced the dimensionality quite a bit, right? We're not making a neural network spit out the entire space-time result. Actually, the only thing that we have here, this nonlinearity, is actually just an R to R function, because it's just applied at every single point in space, just like you'd have with the normal semi-linear partial differential equation solve. So you can actually very nicely represent it as, here's a Fourier series, here's a convolutional layer, just a convolution operation, and with very few parameters be able to discover what the partial differential equation is by doing this post-analysis on the neural network.
Chris, Chris,
Yep.
can you say a word about how you do the sparse thing with a convolutional neural net, just to get row double prime here?
Oh yeah, so this I did it more by eye. You can actually look at it from the CNN weights in this plot, right? In this plot, what I just kind of plotted out, and it shows that so the convolution is just a stencil operation. So the one-dimensional stencil is just a coefficient times u minus one,
Yeah.
coefficient times u, and so then what came out of this training process was, it said all of the coefficients, they add up to 0, which is going to be true for any derivative operator. And the coefficient on the right is equal to the coefficient on the left. And then it's scaled by a constant, which essentially means that it's the stencil 1 minus 2, 1
So
multiplied by some constant.
am I right in saying you have no automatic way to do sparse identification on the convolutional neural net?
I mean, yeah. So right now at this time, it does require that you know a little bit about PDEs, right? But it is something we could probably automate a bit more. Yeah.
Yeah, thanks.
But yeah, so essentially, so that's all been about equation discovery. But what I really want to point out then is that this same idea is not only used for discovering equations, but you can also use it for accelerating equations. So one of the problems that we've been working on a lot for this is with the MIT Caltech connection, called the Klima climate model, where on this for the way that the climate model's ocean model is done is you take a large eddy simulation, right? So one of these LDS simulations, and you try to make a much easier to compute version of it, because if you had to do a three-dimensional Navier-Stokes equation at every point in the ocean, this would be computationally impossible, right? So one way you can do this is you can take a integral along the xy plane, and if you do that in this equation, what you get is you get infinitely many different one-dimensional partial differential equations, but you can close that system by saying, I'm just going to take the first one, and the function that is undefined or would have been defined by the second set of partial differential equations, I'm just going to leave that as something that I learn as a neural network, right? So through this process, you could basically find that this, a diffusion advection equation is a good approximation to one dimension of a large eddy simulation, where if you just find a neural network that is what this missing term is, then you can get a very high fidelity simulation of the one-dimensional behavior out of this kind of equation. And so this is what we did. We train on some sets of parameters, this embedded neural network, which is a function of the current T bar, of the current temperature. And so it's a non-local operator that is learned for the advection. And then what we're able to show is that it's able to extrapolate to new parameters and be able to predict quite well what would happen in other parts of the ocean. But it gives you about a 15,000x acceleration from the 3D Navier-Stokes equations. So there's a preprint out that kind of goes through this in more detail. Though I will say that this project as a whole is not completed yet, because people have done this kind of parameterization by hand. Where you kind of say, here's an approximating function, but I'm going to derive, this approximation by hand. What we're seeing is that this is quite a bit higher fidelity than a lot of the other ones that were done before. To really prove that it's higher fidelity in the context of climate model, we need to finish the integration with the climate model. So right now we have the printout, which is about showing it in isolation, but this is an ongoing project to really demonstrate this in a real application. So one of the interesting things here as well is that a lot of methods for scientific machine learning aren't necessarily able to deal with a lot of the stiffness that comes up. And so actually one of Paredes recent papers on physics-informed neural networks actually highlights that when you have stiffness in your equations, you have a hard time training, pins for circuits on those types of equations. But what we found is that, we found a different variant of this training process of something similar to the universal differential equation. It's not exactly the same, but it's quite similar. But we found that we can make this be able to train on, a pretty arbitrary, highly stiff differential equation. So here is a log scaled version of, for example, the Rober equations. And we're able to show that even on some examples where pins fail, if you use the most stabilized version of these adjoints and et cetera all together, then you get something that can, very much predict the behavior of something that is a fairly stiff equation where you have time scale spanning 10 to the 11th in the coefficients. Now, one of the other things that we found is interesting about this idea is that you can rephrase a lot of other methods that are coming out in this field of scientific machine learning as a form of a universal differential equation. And this isn't really just something like show off, right? Is something to really start showing us that might be the right computational problem to solve. And so, for example, there's a really nice paper that came out by Han Jensen and Wen, which is all about how can you solve these 100 or 1,000 dimensional Hamilton-Jacobi-Bellman equations by essentially taking the connection between the semi-linear parabolic forms and the backward stochastic differential equations. It turns out that if you take their derivation and you omit one step near the end, you can write this down as a universal stochastic differential equation. So you can say that essentially what their method is at its core is it's a universal stochastic differential equation where you have the same neural network in these two pieces, but if you apply Euler-Maruyama's discretization to the stochastic differential equation, and then you arrive at the recurrent neural network formulation that they have. But understanding it as a universal stochastic differential equation then gives you a lot of nice insights, right? Because if you want to ask a question of what is the higher order version of the algorithm, how would you make it implicit? How would you, what is the right way to do adaptivity in these cases? Well, if you write it down as just a differential equation with neural networks embedded within it, and you have, general stochastic differential equation solvers that can work and train on this type of equation, then this algorithm is actually just falls very nicely into just one of the applications of a universal stochastic differential equation training mechanism. And this actually shows up for a lot of the different cases in the literature. So here's another case where you have a multi-step physics-informed neural network, which is actually equivalent to doing a universal differential equation of a specific form, and you just apply a multi-step method to it, and you say turn off adaptivity, make DT fixed. And so there's a lot of methods that are coming out there where you can say, oh yeah, this is a scientific machine learning method, but it's equivalent to a universal differential equation with these options set on the differential equation solver. And so this means that this kind of is telling us that if we solve this one training problem, then we seem to be solving a lot of different training problems, where a lot of the other authors in the field are going to be highlighting the different applications of it. So how are we actually training all these neural networks embedded within differential equation solvers, right? Because that's the one thing I've really been hand waving over. And it really comes down to just adjoints of differential equations. But there's quite a deep story when you talk about adjoints, especially when you start having stiffness involved. So the adjoints of the neural ordinary differential equation, this is the way that it was described in the 2018 paper by Chen, Bettengor, and Duvenon. Essentially, what they say is that you can do an adjoint of an ordinary differential equation by solving the differential equation forward, and then you solve this augmented equation in reverse, which you reverse this ODE so that way you can get the values z of t at the times that you need. And when you are taking these values z of t, you do a vector Jacobian product to be able to calculate the Lagrange multiplier at each point in time. And from the integral of the Lagrange multiplier, you get the derivative of the solution with respect to each of these parameters in an efficient way. So this is essentially one method for how you would calculate these these derivatives. But there's an interesting thing that's going on in the literature, which is really that um, you know some some individuals are saying that, you can do this and decrease the tolerance and, make this really fast. In other cases, you have parts of the literature which are describing that, if you don't do this, if you do this exact method, here's the way that it fails, here's the way that it fails. And really what's going on in the literature is really just identifying that in some cases there's a lot of stiffness inherent in the equations, or a lot of, ill conditioning in the adjoint equations. And really, whether you have this ill conditioning, it really, you have a complete difference in what kinds of, with the method that you have to actually be calculating this derivative. And so here's a nice equation that showcases that, just using the reversibility approach doesn't always work. So here we have a linear ordinary differential equation, where we just say z prime equals minus lambda z, and we just say let's use the differential equation solver to solve it forwards and then solve it in reverse. And let's just make lambda equal 5. You solve it for, my initial condition is 1/2, and so after I solve it forwards and solve it in reverse, I better get 1/2 back out, right? So let's see what happens when you go up to lambda equals 30. It's starting to get a little bit off, but it's numerical error, right? We're fine. What happens when lambda equals 40? Well, now we're off by about 300%. And then what happens when lambda equals 50? We're off by basically 1,000,000,000%, right? So what's going on here is that when you are solving a ODE that is exponentially decreasing forwards, then you're solving an ODE that is exponentially increasing in reverse, and so you have your errors compounding as it grows, and this is something that's known to be numerically unstable. Right, so this is one of these issues that can happen with if you choose the wrong adjoint method. It might be stable in the way that you're actually doing the computation, but unstable in the way that is calculating the gradients. There's actually a more sinister problem that we found when looking at the climate example from before, which is really that for any different differential equation tolerances that we chose, it didn't actually matter. It was actually completely unstable if to use that kind of adjoint. And why did that occur? Well, we can actually pull it out and understand that the behavior by looking at just the linear advection equation, right? So it's a very classic result that if you try to do a discretization of the linear advection equation, right, you have two different choices. You can differentiate forwards or you can differentiate backwards, right? So you have the upwinding version of the ODE, or you have the downwinding version of the ODE, right? So which way should you be discretizing the spatial term to be able to get an ODE? Well, it's a very classic result that says that if A is positive, then you need to be using the upwinding discretization, and if A is negative, you need to use the downwinding discretization, right? So which of these two ways is the right way to discretize the partial differential equation is dependent on the actual parameter A. Now let's think about what happens if you try to do this adjoint approach where you try to solve it forwards and then try to solve it in reverse. Well, if you just try to naively do that to the code that someone gives to you, let's say log A is greater than 0. So they do the smart thing and they use the upwinding discretization. When you reverse their equation, right, the way that you reverse an ODE is you just reverse the sign on the f function, and then you move time backwards instead of forwards. But if you change the sign on the f equation, then that means you now change the A, and so you've changed which spatial discretization is stable, and so you've made it so that way actually this is a case where if you choose a forward discretization that is stable, then you necessarily get one that is unstable in reverse. And so and not only necessarily unstable, but it's actually an unconditionally unstable problem, which means that there's a lot of thought that needs to be going on with the way that you calculate these gradients, because if you just do mechanisms that are in theory correct, you might be missing on and giving something that's numerically unstable. So there are ways to be able to handle this. So for example, you can always make sure that you're only doing forward passes. This is actually a classic method from the Sundial's CVODE suite. Or another way that you can make use of do this as well is that you can use what's known as discrete sensitivity analysis, which is actually equivalent to doing reverse mode automatic differentiation of the solver code, where the solvers it's a reverse mode automatic differentiation of the solver code, where you keep the PI, the time step controller constant with respect to the reverse mode automatic differentiation. And you can actually prove in this case that the what you call the discrete sensitivity analysis, which is this process for computing the gradients, is actually always going to give you a consistent discretization of the differential equations. So there's really two worlds of neural networks and ODEs. So what we found from our users is that there's a group that's doing this for machine learning. So the neural ODEs paper at NeurIPS was really about how do you do image processing with an ordinary differential equation. And so they have a very different problem then, because the learned differential equations are just maps, and so you can actually do things like regularization to be able to choose an easier ODE to fit. Um, and also the whole ODE is a neural network, and so it's easy to GPU. Whereas in the SciML world, we actually have completely different performance characteristics, where if you do regularization, you're necessarily going to be biasing the result of the learned part of the dynamical system, and so you will actually bias the mechanisms that you're predicting. Another thing is that you can't just choose to learn an easier ODE, because if you just say, I'm going to regularize out all the stiffness, you might not necessarily capture it and predict, and learn the correct equation. And um, one of the really interesting things that we found is that there's this mix between GPUable code and non-GPUable code, right? I'm not going to go into the whole details about SPIMD programming, but when you write down a differential equation like du of 1 equals u of 1 times u of 2, when you do that indexing, that kind of code is very much not GPU compatible, while the neural network portions of the code inside of there are. And so what we've really seen from this is that even though there is a world that is doing neural ordinary differential equations, neural ordinary differential equations in the machine learning sense and in the SciML sense have actually completely different performance characteristics, completely different adjoint methods to apply, and they essentially need completely different methods, because it's as different as non-stiff versus stiff ODE solvers. And so what we had to do then was we had to create a whole set of adjoints that handle every single case. And this kind of spans the field. If you look at the derivation of the adjoints, this kind of spans all the different possibilities that you can have in there, where you can have things reversing, you can have direct quadrature done of integrals, you can have quadratures embedded in ODE solvers. It's essentially, if you lay out a chart of all the different ways to calculate each of the terms, you'll find that this is essentially that whole set. And each of them have a completely different performance behavior, right? So the reason why the version that is solving in reverse is used so widely in machine learning is because that can give you O of 1 memory usage, right? Because if you never have to save the time series of the ODE, then you only ever have to save the current state, then it's a fairly efficient method. But you can't use that when you actually have PDE discretizations, or if you have a high Lipschitz constants, which is another thing to say, a stiff differential equation. But then then you can make use of other methods in the cases of stiffness. And so what actually ends up being the most efficient method highly depends on what kind of problem you're looking at. And one last little detail to throw in there about how the neural networks that are embedded are actually trained is the fact that when you have a vector Jacobian product, a vector Jacobian product itself is the primitive of reverse monatomic differentiation. So if you do reverse monatomic differentiation, the way to be able to calculate this in O of 1 time instead of being able, without having to build the Jacobian, is to push forward with the function f, and then you do the pullback of the the reverse monatomic differentiation pullback with the pullback vector being lambda. And so normally when you do reverse monatomic differentiation, you usually just stick 1 in at the end and you pull back the value 1. That gives you back the gradient. If you actually pull back this lambda, then what you actually get is a whole vector Jacobian product without the Jacobian being built. And so then there's this whole layer of, you have all these different choices of adjoints which are dependent on the problem, but then actually dependent on other aspects of the problem. You might want to use different versions of reverse monatomic differentiation to be able to calculate just this term within the adjoint highly efficiently, efficiently for very large terms or efficiently for small terms. And there ends up being this whole kind of choice matrix which really comes into play. And so this is really what the Diffie-Flux software handles. It basically has all of these different methods for doing the vector Jacobian products and adjoints together. So that way, each of these problems are solved with stiff method, with implicit methods, multi-step methods, strong stability preserving methods, Rackauckas-Chebyshev methods. You take any of these possibility solvers, you stick them with any of these adjoints and with any of these VJPs, and you get each of the combinations. And each of the combinations really has its own purpose where it comes into play. Um, let's see. I'm at the end here, so I always like to show it at the end, just a few benchmarks. So even though this is something that's written in a high-level language, you can show that it compiles to since Julia ends up actually being compiled, all the code that we're working on here has actually been it's been worked on for years to make sure that it compiles to something that is more like a C++ or Fortran library. But if you actually look at the details on a lot of non-stiff equations, you'll find that there's methods in this library that you won't find in other cases. So for example, there's some methods from the late Jim Werner, which are very, very highly optimized high order Rackauckas methods, which you can see in this work precision plot. So for the same time, it takes less error than even classic methods like ODEX or LSODA or or OD DOP A53. And so that's on non-stiff equations, but you also find that on a lot of stiff equations. This has been a development over the last 2 years or so. A lot of the most efficient methods on a lot of equations will be methods that are only found in these pure Julia solvers. So you can take the most efficient methods you can find, stick a efficient adjoint method on it. One of the problems that we're trying to solve recently is how do you actually help someone automatically find what combination there is in this exponential combinatoric space of options to choose. But there is something, at least what we know is that we have like an existence proof that there is something that is very efficient in this set. We just need to help you find it at this point. So yeah, and so the adjoint process itself is essentially fully automated at this point. So if you write a differential equation code and you then run reverse mode AD over it, you just have to tell it what sensitivity method to use, and it will automatically write the code in there. So you don't need to really worry about using. You just use the differential equation library directly, and everything about the adjoints is handled kind of behind the scenes. And so this is really the first library that we have that has this integration with reverse mode AD for the fast vector Jacobian products, but also has all the tools that are required so to be able to solve the stiff equations and do the the stabilized adjoints for stiff equations. So I mean, you have had methods before that are able to do this on stiff ODEs. So for example, CVODES and PETC's TS are able to handle stiff differential equations, but they don't have that direct integration with reverse mode automatic differentiation to be able to do the O of 1 calculation of the of the adjoint terms. Whereas the methods that are coming up in the machine learning world have all been built for stiff equations, and so to be able to solve all these problems I described earlier in the talk, we built out the system that has all these different combinations to be able to use the fastest methods that are possible with reverse mode integrated into it with all of the methods for stiff ordinary differential equation solving. So yeah, I'll take questions at this time. If you want more information, there's a bunch of videos that you can find on YouTube all the time. For example, there's a 4-hour workshop which goes through live coding exactly how to do a lot of these examples, just start to finish, just typing them all out from scratch. And then if you're more interested in the methods in more detail, this year I taught a graduate course at MIT. It's MIT's 18337 Parallel Computing and Scientific Machine Learning, and all the details, all the lecture notes are up there, along with all the YouTube lectures that took place this year. So yeah, I'll take any questions at this time.
Okay, thank you, Chris. Questions? You can just unmute your mic and speak up.